You learned how to do Lewis structures at some point in your previous history, so let's review exactly how you should generate them for an inorganic compound like sulfate. First, if you start by counting up the total number of electrons, you're on the right track. And there's really three components that bring electrons to sulfate. We have one sulfur atom, we have 4 oxygen atoms, and we have 2 minus charges overall. So these are the total number of things that bring electrons to the party. Sulfur brings 6 electrons, oxygen does as well, and each individual charge is 1 electron. So the total number of electrons that we have for our system is 6 from the sulfur, 24 from the oxygen, and 2 from the charge, for a total of 32 electrons. So when you go to actually generate the Lewis structure itself, you have to start by putting the central atom in place. And in this case, it's pretty obvious. Sulfur is the only thing that can serve as a central atom. And you know that because that sulfur is a good choice for the central atom because it is the most electropositive atom. It is the least electronegative atom. And or another way of thinking about it is that sulfur can make the most bonds to other things, whereas oxygen prefers to make 2 bonds. So anyway, sulfur is going to be in the middle. Then we need to surround that sulfur with all of the various oxygens that might be involved. And you'll notice I'm starting to draw this in a strange way already, but I'll explain why I'm doing that in just a second. Okay, so I've got 4 different oxygen atoms. There they are around the sulfur. How many electrons have I used up? Well, each one of these bonds has 2 electrons in it, and I have 4 bonds, so that's 8 electrons total. I need to put in the rest of the electrons. And I start by putting all of the electrons around the periphery, so each oxygen, I fill up its octet first, and then I see where we stand. So each individual oxygen now has 8 electrons surrounding it. So this oxygen is happy with 8 electrons. This oxygen has 8 electrons. This oxygen has 8 electrons, and so on. How many electrons have I used total? All 32 electrons. The primary rule of Lewis structures is to make sure that everything has a full octet. Everything does have a full octet around the outside, but notice that the sulfur also has 8 electrons around it, so everything is currently happy. Is this a valid Lewis structure? Well, not yet, because I haven't done the formal charge. The best way to think about formal charge, for me anyway, is to imagine cutting each of these bonds in half. The sulfur has 8 electrons around it, but I'm going to administratively assign 1 electron from each of the bonds to sulfur. So how many electrons does sulfur have? It has 8 electrons surrounding it, but that's kind of boring because it's the octet rule. When I'm trying to think in terms of formal charge, I don't care about how many total it has. I care about how many the sulfur can claim as its own. And in this case, the sulfur has 4 electrons that it claims as its own. Sulfur brought 6 electrons, so that means that sulfur is short 2 electrons, so the sulfur has a 2+ charge on it. What you want to do is count up the total number of electrons around the oxygen. So there's 6 electrons because of all the lone pairs. 1 electron from there, so it has 7 electrons. It wants 6 electrons that it brought with it, which means that it ends up having a single extra electron, which means it has a minus charge. Now this oxygen also has a minus charge. This oxygen also has a minus charge, and this oxygen has a minus charge, all because of the symmetry. Each one of those oxygens is the same. What is a valid Lewis structure for sulfate ion? Well, there it is. Each individual oxygen is a -1, the sulfur is a +2, therefore overall what we have is a -2. So what I've done so far is all fine and dandy, but I could improve things as long as the sulfur can have an expanded octet. So right now I have lots of formal charge. Each oxygen is minus when it'd rather be neutral. The sulfur is very positive, it would rather be neutral. Can we solve this? Yes, we can, as long as the sulfur, which is in the second row of the periodic table, can have extra electrons around it. So you may have thought of resonance already by pushing electrons onto the sulfur. So these arrows that I'm drawing show movement of electrons. This lone pair will make a double bond. That lone pair will make a double bond. Why have I chosen to use 2 lone pairs to make double bonds? Because that will give the sulfur 6 electrons total. So let me now draw what this will look like after I push the electrons onto it. Alright, so now each of the oxygens has donated a lone pair, and now we've got 2 double bonds to the sulfur. What is the formal charge on the sulfur? Well, if I administratively assign 1 electron in each bond to the sulfur, then you can see I have 1 electron each from these bonds. So 1, 2, 3, 4, 5, 6. 6 electrons on the sulfur. It brought 6 electrons. Therefore, the sulfur is content. How many electrons does this oxygen have? 1, 2, 3, 4, 5, 6. Again, it brought 6, so this oxygen is content. By the same token, this oxygen is satisfied as well. Keep in mind, of course, that not all oxygens have been made happy by this process. This oxygen has 7 electrons around it. It wants 6, therefore it's minus. 7 electrons, it wants 6, therefore, again, it's minus. When I have drawn this, what I have drawn is a resonance structure where the electrons are now distributed slightly differently in the pi framework of the molecule. So what that means is that I now have still a 2- charge. I haven't done anything except shove around where the electrons are in the double bonds, the pi framework of the molecule, as opposed to the single bond. When you are drawing resonance structures, you are allowed to move where electrons are relative to the pi framework, but you're not allowed to break any single bonds, break any sigma bonds. This is 2 different ways of representing sulfate. This is one where we are constrained to only have an octet around the sulfur. If we can expand the octet, then we can have structures that look like this. My choice of which oxygens to have the double bonds was arbitrary, so I can draw other good resonance structures. This pair of electrons might be one that kicks down and makes a double bond, which might force this pair of electrons to stop being a bonding pair and become a lone pair once again. Let me draw what that looks like. This is a different arbitrary distribution of the electrons. Notice I have 2 oxygens with double bonds in both structures, and I have 2 oxygens with single bonds in both structures. The ones with single bonds end up with 7 electrons around them and a minus charge, so that means that those 2 have minuses now. The ones with double bonds, as we saw before, are neutral. The sulfur itself, of course, has 6 electrons surrounding it, and it brought 6 electrons to the party, so it is happy as well. I had an arbitrary choice of which electrons to move, so I could just as easily have chosen to make this oxygen kick electrons into the system, and that bonding pair of electrons go on to that oxygen instead, which would lead to different resonance structures. So keep in mind that there are many resonance structures available. If you count up all of the possible resonance structures, you will end up with a large number of them. And they're all equivalent. In all cases, what you should have is 2 oxygens that are doubly bound, 2 oxygens that are singly bound, 2 oxygens that have 2 minuses on them, 1 each, and 2 that are happy, as well as the sulfur being happy. So in all cases, you end up with a 2- charge. It's just a different way of representing the molecule overall. Why did I choose to draw the molecule in this shape as opposed to the standard 2-dimensional drawing that you might have expected? Here we have the classic way you might have chosen to draw the molecule in the first place, with 90-degree bond angles implied between each pair of oxygens with each other. Just to check our formal charge, let's review again. 4 separate electrons that belong to the sulfur. The sulfur wants 6 electrons. That makes it a 2+. 7 electrons around each oxygen. Each oxygen wants 6 electrons. Therefore, this is the same, is equivalent to this structure right here. However, this implies 90-degree bond angles between those, whereas this structure is implying something a little bit different. In fact, I should go ahead and redraw this with the right bond angles to show you what this will actually look like. So I've now cleaned up the formal charges, and I've also indicated with the wedge that this oxygen is coming toward you out of the plane of the board, and this oxygen with its dash is pointed back away from you into the plane of the board, into the wall. So the reason why we would represent the molecule this way is because this molecule will actually be tetrahedral, and every single one of these bond angles is going to be 109.5 degrees. So each of these bond angles is all going to be 109.5, and this is the right way of drawing the molecule that implies that it's tetrahedral, as opposed to this representation, which implies, of course, 90 degrees. Basically, this is the 3-dimensional way of thinking about the molecule. This is a 2-dimensional way of thinking about the molecule. Is this a valid Lewis structure? Yes. Is it fine to represent molecules this way? Sure. But I'd like you to get into the habit mentally of thinking in terms of VSEPR. When you have a central atom with 4 things bound to it, 4 bonding areas, that will be a tetrahedral molecule, and you might as well start practicing thinking about it as a 3-dimensional object, a tetrahedron, rather than something that is square and planar. So please start thinking in these terms as we work on our Lewis structures. But okay, this class is organic chemistry, so what I just did was an inorganic molecule. If I want to do Lewis structures for organic molecules, what you'll quickly realize is that I'm almost always going to have carbon as the central atom, so there it is, and now I should arrange the 4 things around it, and I'm kind of cheating in a sense by using hydrogens as the other thing, but what that shows us is the simplest possible organic molecule will be arranged this way. A carbon in the middle, 4 things around it, and therefore it's going to be tetrahedral. What are the bond angles in a tetrahedron? Well, they're going to be 109.5 degrees. I have chosen to draw it this way because it represents the tetrahedron very nicely. When you have a carbon atom, you will always count to 4 around it if you can. So this is a perfectly valid representation of an organic molecule, and this is a perfectly valid Lewis structure, and it's as easy to write down as that. When I go to write down oxygen-containing Lewis structures, almost always you should think, hey, this is going to be a lot like water, and much like the CH4, the simplest possible carbon-containing molecule, the simplest possible oxygen-containing one is just plain water. And again, you could just write this down by inspection. The oxygen is going to have all 6 electrons that it brought to the party. The hydrogens are going to each bring 1, therefore 8 electrons total, and that's the perfectly valid acceptable Lewis structure for water. This, again, I've tried to draw roughly in tetrahedral form. As it turns out, this bond angle is something closer to 104.5 degrees, and that's because these lone pairs exert an outsized influence on the molecule and force those 2 hydrogens closer together than they might otherwise be. We'll talk about that more in VSEPR discussions. This is the best way of representing the molecule. How many electrons did carbon bring to the party? Well, it always brings 4, and it always wants to have 8 electrons total, so it always wants to have 4 things around it. Administratively, it always ends up with 4 electrons. Okay, nitrogen. How many electrons does it bring? It brings 5. 3 from the hydrogens. Therefore, again, if we want to do this very quickly, you end up drawing something that looks like this, and bearing in mind that nitrogen will be tetrahedral, but it has a lone pair, then the standard nitrogen Lewis structure is one where you end up with a trigonal pyramidal structure and a lone pair. And again, the nitrogen is happy when it has 3 things bound to it. So there's one last bit of thought that I want you to put into these very simple Lewis structures, and that is carbon always wants 4 bonds. Carbon's probably going to be unhappy if it has even a single lone pair, and it's going to be unhappy if it doesn't have 4 bonds. Oxygen, what does it want to have? It wants to have 2 things bound to it, 2 bonds, and 2 lone pairs. If it has 3 things bound to it, it's probably going to be unhappy. If it has only 1 thing bound to it, it's also going to be unhappy. Same thing with the nitrogen. Same idea, I should say. It wants to have 3 bonds and a single lone pair. Deviate from that canonical example, and all of a sudden the nitrogen's going to be unhappy. So what happens if I go to add a single additional hydrogen to a water molecule? Well, this is going to make a bond to that hydrogen, that additional H plus ion. And what you end up with, after it rearranges structure to find the lowest possible energy, is a trigonal pyramidal structure with 3 hydrogens bound to the oxygen. Keep in mind, of course, that this oxygen now has 3 bonds and a single lone pair. So how many electrons does this oxygen have? 1 from this bond, 1 from this bond, 1 from this bond, 2 from the lone pair. It has 5 electrons. How many does oxygen want to have? It wants to have 6. Therefore, oxygen is unhappy. Now let's pretend I have an OH minus floating around out here. How do I know it's an OH minus, by the way? It has 1 electron from the bond, 6 from the lone pairs, therefore it has 7 electrons total. That gives it a minus charge. So what happens if an OH minus encounters a water that happens to be floating around nearby? Well, it's going to pull off one of those H's and swap. So this will now become the water, and that will become the OH minus. The point I really want to make here is if oxygen has 2 bonds and 2 lone pairs, it's happy. If oxygen has 3 bonds bonds and a single lone pair, then it is plus charged and unhappy. And if an oxygen has a single bond and 3 lone pairs, then it has a minus charge and it's unhappy. The moral of the story is that oxygen would love to have 2 bonds, 2 lone pairs. Simple as that. By the same token, if you add an extra hydrogen to a nitrogen so that it has 4 bonds, it's going to end up displeased with things. It will go to be a tetrahedral but plus charged thing, because all of a sudden, if you administratively assign the electrons, you find that the nitrogen now only has 4 electrons and the nitrogen wants to have 5, and therefore it is unhappy. By the same token, take a pair of electrons away from that bond and give it to the nitrogen, and now you'll find that this nitrogen has 6 electrons, and therefore it is minus and unhappy. So if you are thinking about Lewis structures from the point of view of an organic chemist, there's a lot of shortcuts that you can use, and mentally the easiest one is carbon always wants to have 4 bonds, oxygen wants to have 2 bonds and 2 lone pairs, nitrogen wants to have 3 bonds and a single lone pair, and it's really as simple as that. You want to get to the point with Lewis structures that you can simply write them down very, very quickly without even really thinking about them all that much, and the easiest way to do that is to just have this sort of mental shorthand in the back of your head, but then check after the fact when it comes to the number of electrons that you distributed. And now I'll show you the problem with Lewis structures, or at least a significant problem with Lewis structures in organic chemistry. Here is a perfectly valid molecular formula: 3 carbons, 6 hydrogens, 1 oxygen, and I say to you, go. Please make me a perfectly valid Lewis structure, a molecule that represents all of that. Well, what you might decide to do is to end up drawing something that looks like this, because this is a very quick and easy way to solve things. I'm going to have 6 hydrogens surrounding these carbons on the edges, 1 carbon in the middle, and a doubly bound oxygen there. Is that the only structure I can use to represent this? No, I could choose to do things slightly differently. I could instead put the double bonded oxygen on one side. So I haven't drawn out all the hydrogens. Said another way, I can't tell based on a molecular formula what's going to be valid. Let me draw a couple other shorthand versions that might work to fulfill the structure. Again, I'm not drawing where all the hydrogens are, but there's 3 there, there's 2 there, there's 1 there. What's the simplest rule to understand how many bonds are surrounding each carbon? Well, each carbon wants to have 4 bonds. So this is what's over there. So I could choose to draw this out, but it ends up taking a lot of time. So I'm really going to stop drawing simple Lewis structures now, partially because they're not as useful as you'd like, partially because they take a long time. What's over at this position? Another hydrogen. What's at this position? 2 hydrogen. There they are. Okay, can I draw anything else that would be valid? Sure. I could put a double bond in there somewhere and draw an OH that looks like that. I could put a double bond somewhere else and put an OH out there, and so on and so forth. All of these are valid Lewis structures. But you will notice that you have to be able to simply write down Lewis structures and get them correct without thinking about them. But notice as well that I'm not even drawing good Lewis dot structures anymore. What am I missing here? Well, I know, because this is always going to be true. Oxygen wants to have 2 bonds and 2 lone pairs. Oxygen wants to have 2 bonds and 2 lone pairs. 2 bonds, 2 lone pairs. 2 bonds, 1 to the carbon and 1 to the hydrogen. Maybe I should draw that out. And 2 lone pairs. There are 2 lone pairs on this oxygen as well. And so on and so forth. So, Lewis structures are the foundation of everything we do in organic chemistry. But they stop being useful for organic chemistry really, really quickly. Except, Lewis structures are still useful, and the ability to generate a Lewis structure and know whether it's right or not remains useful the entire time. This is a condensed formula, a way of representing organic molecules that gives you a little bit more information than just the basic molecular formula. I could represent this C2H4O2, but that contains less information than this. This suggests the way in which the molecule will be drawn out. So what I want you to see now is I can quickly draw something that's representative of what that is trying to show. This is the Lewis structure, once I fill in the dots, for the molecule. And what I would like you to be able to do is to generate that very quickly like that. But I also want you to be able to instinctively know whether you have gotten it correct or not. How many electrons are around this oxygen? Well, 2 bonds, 2 lone pairs, that means it has 6. It wants 6, so it's happy, it's neutral. 2 bonds, 2 lone pairs, this oxygen's neutral. This hydrogen has a single electron that it brought, and it remains with 1, so it's neutral as well. This carbon has 4 bonds, just 1 ones I've drawn. This carbon right here also has 4 bonds, only one of which I usually tend to draw because the 3 hydrogens there are implied. You should be aware that this carbon has no hydrogens because it has 4 bonds to other things. So keep that in mind. I would like you to be able to just sum that up that quickly. There's something else that I'd like you to be able to do as well, and that is to highlight almost as fast as that what the hybridization for each of these atoms is. So this carbon right here has a tetrahedral shape to it, and I've done a relatively bad job of drawing in the geometry that convinces you it's tetrahedral, so let me fix that. There it is, it's tetrahedral now. And since it's tetrahedral, I know that the orbitals that this carbon is using to generate all 4 bonds must include an S and all 3 Ps, so that's an sp3 hybridized carbon. This carbon only has 3 bonding areas, which means that it's trigonal planar, which means that this is 120 degrees. It means that this angle is 120 degrees. It also means that this is going to be sp2 hybridized. This oxygen, because it's making a bond with that carbon, a double bond with that carbon, it needs a leftover p orbital for that double bond. It as well is sp2 hybridized. This oxygen is only making 2 single bonds, so it is sp3 hybridized. The hydrogens are always boring. They are using their single 1s orbital to make the bonds. But I'd like you to be able to size this up at a glance. I would like you to be able to tell me right away what the hybridization of each of these atoms is. I'd like you to be able to tell me that these bond angles here for the tetrahedral portion of the molecule are going to be 109.5. I'd like you to be able to tell me that the bond angles for the sp2 hybridized structure are 120, and so on and so forth. All of this stuff is material that you've learned at least in Chem 110 or 190 here at HWS, and probably before that, and this is stuff that I expect you to have instant recall over. You need to be rock solid on all of this stuff in order to move forward in organic chemistry. This is knowledge that I'm assuming you already have. So the global message from Lewis structures is that you need to be able to generate inorganic Lewis structures very, very quickly and easily, but we are almost certainly going to stop worrying too much about generating good Lewis structures, and instead we will be generating organic shorthand. We will be generating the line angle Lewis structure. So rather than drawing the molecule out this way, what I'd like you to be able to generate instantaneously, but then be able to interpret and know exactly what it means, is this line angle structure. You don't need to draw out the implicit hydrogen. This is shorthand. This is better. You don't necessarily need to draw out the lone pairs that go on each of these. However, later in the course, you're going to need to know that the lone pairs are there, so sometimes it will be good for you to draw out those lone pairs explicitly. You should sometimes need to draw out implicit hydrogens as well, but as a general rule, stop drawing them. Just know that they exist. However, I will also caution you, it's almost always a good idea to draw out OHs that way rather than what might seem like a natural thing to do, and that is to draw OHs this way. Frequently, those are the hydrogens that are reactive, and so it will almost always help you to draw them out this way. Just get used to generating this as the common structure. Practice those Lewis structures. Get good at them. Get to the point where you immediately know if a Lewis structure is wrong. That is the foundational aspect of organic chemistry that we need to ensure that we are good at.